All right, let's look at an example. Part A wants us to approximate the sum of this series 1 over n cubed, which we know this series is convergent by p series, because p is bigger than 3 there, using the sum of the first 10 terms. Well, we can do this on our calculator for part A. We want to find the sum of n equals 1 for the first term to 10 here, to 10 of 1 over n cubed. So what is this approximately equal to? You can do this on your calculator, and how you do that is go to the math menu. If you go all the way to the bottom, there's going to be one near the bottom called summation. Select that. The first thing you need to do is enter in your variable. So hit your variable key. I'm in function mode, so put x. If you're in series mode, it should put n in there. It doesn't matter. Do 1, and then hit your up arrow to put your upper number in of 10, and then hit over the right over arrow key to put in your series 1 over and 2. And if we hit enter now, it should give us the sum of these first 10 terms. So the approximation here is that it's equal to 1.753. So there's our approximation. All right, now there's another part to this. It says estimate the error involved in this approximation. So what we're going to do next is we want to look at what is our error, our remainder error. It's going to be less than or equal to our n value, which for here is 10 to infinity of the integral. So we're going to go back now and figure that out. So r of 10 here is going to be equal, or sorry, less than or equal to the integral from that same n value, so 10 to infinity of r 1 over n cubed. And because we're changing this, I'm going to change x rather than x, since we're changing it to a integral. So now we're going to solve this out and see what we get. The antiderivative of this one, probably easier to think of this as x to the negative 3 when finding an antiderivative. So our antiderivative here is going to be go up a power negative 2, reciprocal negative 1/2. We're doing that from 10 to infinity. So keep evaluating here. We're going to need a limit to do this one, so I'm going to use the limit as I'm going to use the variable t here. Approaches infinity of this. And I'm going to write this as 2 over x squared here. So if we evaluate, now we have the limit. This 2 goes to infinity of negative 1 over 2t squared. Minus the opposite value of this over 10 squared. Okay, so evaluating now our limit. If this is going to infinity, if t is getting really big, that's going to be a really big number squared times 2 even bigger. If we got 1 over a large number, that's all going to 0. So our percentage in US is 0. Our other one here, we got minus and negative, so we know that's plus. And then we got 10 squared, which is 100, times 2 would be 200. So this is going to be plus 200. So it looks like our remainder here is going to be less than or equal to 1 over 200. Or another way of saying that, if you do 1 over 200 calculator, 100, that this is within 0.005 of the actual answer. So our approximation that we had up there is within 0.005 of the actual. That's our That's our error. So it's at most outside that much. So we know within the first two decimals of this, to be like the infinite sum should be within that. The rest of our decimals, we don't know how accurate those are, because at most this is accurate to infinity. All right, now let's look at part B. How many terms are required to ensure that the sum is accurate to within 0.0005? So now they added another zero in there. How many terms would we need to know that our sum is accurate to within that much? Okay, so here now we're going to kind of do the same thing, but work the other way. So part B, we want our error to be within here 0.00. Within that, how close? So again, r of n, we're not sure what n is on this one. Should be less than or equal to our integral from n to infinity of 1 over x cubed dx. So if we do our same solving here, we know that we're going to get an antiderivative that we got last time. We got the limit t goes to infinity, and our antiderivative to this, and could be from n to infinity. So if we, okay, so now if we plug in those values, what we're going to end up with is that r of n here is going to be less than or equal to c goes to infinity of this and just like before, you know, this is going to be 0, and that's positive. So what we end up with is that our n is going to be less than or equal to 1 over 2n squared. So if that is what our r of n is, and we want to make sure that this ends up being less than or equal to, they asked us to do it between 0.005 and 2. We want to make sure it's less than that. We want to now solve this out. So what n value is going to make this true? So to solve this, let's start by multiplying both sides by 2n squared. That'll get rid of our denominator down here. So now this side, if we do that, we just have 1. On this side, we're going to have 0.0005 times 2 n squared. So if we do that on a calculator, 2, this is 0.001 n squared. All right, well, we want to keep solving. Now let's divide both sides by 0.001. Now this side is going to be n squared. So if we do 1 over another, 1 over the previous into copy and paste that, and we get 1,000. So now we know n squared here is greater than or equal to 1,000. Now let's divide here, or sorry, not divide. Let's square root that, and we can find our answer. So I'm going to write this, open side circle. Let's square root. So if we square root, then n is going to be greater than or equal to whatever this comes out to be. So let's square root 1,000. And if we do that, it looks like we get 31.62. All right, so we need an n value greater than or equal to that. Since that's not a whole number, it looks like we're going to have to use 32 terms of this. Add up the first 32 values in order to make sure that our answer comes to be within 0.0005 of the actual answer. So we'd want to, we're doing our limit here. We wanted to do this to make sure we're accurate to within that much. We want to do the first 32 terms of this to ensure our error is less than